All right, how we doing, everybody? Doing good. We feeling alive. It is the final push. Today's lesson is going to be more of just going over some miscellaneous things or some fun facts about CMOS. Or let me see. What's my password? I miss Jake Bake 123. What's his name? CD EE 420 lab. Everyone knows how I did this magic trick right here, right? If you type in E and then press tab, it does that. Okay, that's just a fun fact. And then if you just press the up and down button, okay, history, okay, quick little Linux tutorials, okay. When you go to your job and they say requirements, need to know Linux. All they're asking for is, can you do what I just did there? Okay, they just want to know if you can cd, move, remove, or create directory, make directory, little things like that. ls, okay, how to copy paste. So as an EE, yes, you do need to know coding, but it's like really minimal, just really basic stuff. So should I look at stuff? Let me see. Oh yeah, I'll talk about this. Let me see. Micron jobs. I want to do something fun for you guys. Idaho. Huh? I don't know. Maybe. I just want to show you guys what guys can do. Search jobs. Let's see. Search jobs. Let me see. Process integration lead. Ooh. DRAM. DRAM design engineering. We call it. What other jobs? Oh, is that it? Research and design, thin films process. Ooh, cute. And then let me see. Minimum qualifications. Let's see. Does it say anything about coding? I don't think it does. Well, let me click on this staff design verification engineer. Responsibilities: verify DRAM. What do you call it? Leap design projects and mentor junior design or junior engineers. Let's see. Understanding of CMOS circuit design, mixed signal verification. Ooh, look at that. Experience with HSpice, Verilog, HDL, scripting languages, system Verilog. So I think this is stuff that isn't this what do you call it? You guys did Verilog stuff in 421, right? Yeah, I want to re-strengthen that. I'm gonna create new content for 421 Lab to prepare people for a job like this, because I think for DRAM you don't build it by like hand like the way we do it in this class, but you code that. Okay, so I want everyone by the end. Everyone should be able to meet this minimum qualification 421. Let me see. Um, Analog design IC design engineer jobs. Okay, I'm just going over. Ooh, Intel. Look at that. Apply on LinkedIn. Nah. Let's see. Qualifications: bachelor's degree in electrical engineering with 4 years of analog experience. And benefits, responsibilities. What other things are in here? Is there any minimum? What else is there in here? And then, oh, look at this. PhD in electrical engineering with 6 months of professional experience. You think I qualify maybe? Nah, I don't think. Well, I do, but I don't know if I'm going to go for it. But anyways, analog IC design engineer, Apple. Staff engineer at analog devices. Look at all these yummy jobs, okay? And this is what we're trying to prepare you guys for, to hit these jobs, 420, 421. So look into that, okay? So that was just a little thing, and then I'll talk about this. Anyways, everyone saw those final projects. Not the final projects. Oh, here's your due dates. Current is still due tomorrow midnight, because I gave everyone about pseudo 3 weeks to do it with me. You guys watched the videos. You guys saw the headaches and all that pain that I went through to make sure that assignment looked nice. Nice tutorial, right? But yeah, some people were getting weird. Maybe I don't know how. Well, I'll try to see if I can generate that. Uh, did you figure it out?
Yeah, I already figured it
What
out.
was the problem?
So for my LBS setup, I put convert into geometry, but not
The
geometry
geometry
plus
plus
text.
text.
Yeah,
You
that's
see,
gonna
little
be a
things.
problem.
Little lab two. When I tell everyone, I please turn on these assignments, and if you don't do assignment X and you do assignment X plus one or whatever, you're not gonna have a good time because I don't like wasting work. Everything you do, assignment one. Actually, let's okay. I want to build this confidence in you guys to tell me if I'm a good professor or not. Okay. Today's like a review. What's this? NMOS and PMOS simulations. What's the thing you learn? How to simulate analog design environment. You know what? I don't like when Cadence does this weird thing. Anyways, lab one. There you go. Analog design environment. I teach you how to use that tool. Okay. If you don't know how to, if you skip this assignment, consider yourself, I don't know, auditing or I don't. This is like the bread and butter, okay, of the class. You can't have the PB without the sandwich, or I don't know, PB and J sandwich. Anyways, what's assignment 2? Layouts. And what do I teach you guys to do? Yep, how to do layout. DRC, creating layout cells. That's the entire assignment, okay? If you skip this one, consider, I don't know, something. Because I don't like wasting work. I put valuable resources, valuable time. I'm a student just like you, and I'm no BS, and I want to make sure you guys can go home and be like, man, David was a worthwhile guy, or man, that David guy put us to work. But I did learn something, okay? Like me or hate me, I'm just here to make sure I do my job and give you guys what you want. Lab 3, RC filter design. What did I make you guys do? Let's see, let's zoom in. AC sims, right? Transients, right? How to use the calculator. How to use a capacitor, which this assignment needs to be re-edited too, because I think after assignment 4, I want to redo assignment 3 because that sub pin was just so weird. Let me just click on, let's see. Do you guys like these things right here? If you click on the hyperlink, boom, tells you how to do it. Actually, I don't like this. Let me see. I have another hyperlink I like. Like this figures. Let's see. Where's the answer to the homework? Our low pass, what do you call it? Low pass filter schematic. Click here. There it is. And that's your answer. But I want to know what I did here because I think I did like a 2-terminal thing. I don't remember what I did. No, it was the mim caps. I didn't do the mim caps. Okay. Let me see if I did that here. Yeah, MOS cap operation. And no, I didn't make you do mim caps, but anyways, assignment 4, which is due tomorrow. Okay, Hermiers, and what did I teach you guys? How to what's his name? Do times 5. The difference between the times 1 and the times 5, you just change the finger or the multiplier. Okay, not that hard of an assignment. I'm really chill. Just for the times 5 one, you just got to do a little extra work. Like just a little bit of work. You see here, is that hard? No, it's just I'm just showing you guys what's worth it. And someone's gonna say it's too much tedious work. And yes, I don't blame you. It's tedious. You got to start this the day, like as soon as you can, because if you start doing this the night before and you're like, oh, I'm gonna put this class as a back burner, that actually hurts me personally, because I put a lot of like blood, sweat, and tears into like all the other labs. This one right here, I love this class. I would have loved to put give you guys another 3 more assignments. We would have talked about transmission gates. Oh, that one I want to show you guys. Maybe how to use build a special circuit, like I don't know, some cool special final project circuit. And what will be another thing? I'll see the baker, but I want to show you guys more cool techniques. I think there was like build your own transistor without using a P cell. That's super cool. So basically, you have a huge freedom to like make this big waffle of like NMOSs and PMOSs just so squished together. It's super cool. So then it can look like something like this. What do you call it? Transistors. I don't know. Let's do 28 nanometer process or something like that. Yeah, look at this. Cute, right? Stuck all together. Now let me see. Because I would assume these are transistors. This looks like a via. What else is there? Is that a good picture? Transistors, IC layout. Is there a good one? Ultimate guide to IC design. But yeah, point is you can look at these things. You see transistors under microscope. There we go. Much better. Yeah, stuff like this. You see, you can start understanding what's going on. Those little dots, those are vias going underground, and you see, you can start seeing what's going on. Transistor gates. That's more important. Yeah, let me see. There's a lot. Oh, I think this is a better one. Yeah, you see gate, right? That's a gate, poly, and then that's a tap, boom, and then okay, let's just think this is VDE right here, right? It's going up the water, or this is a gate. Anyways, gate. This looks like a via, another gate, and this is doing something pretty cool. Anyways, let's see what else is there. There's no good pictures. Everyone's doing the funny. Oh yeah, you see this right here? Gate, source, drain. It's some cool stuff. Okay. Long story short, that's what I showed you guys there. Assignment 5, multi-channel circuits. Okay, and what did I show you there? Just how to do what's his name? Oh, did I? I didn't even put the things in here. See, that's where I did a bad job. My fault. Just how to show you guys how to do busing. Okay, busing is very good, very important, especially if you're doing like CP stuff and you have what do you call it, 64 wires or 64-bit bus, or let's just say 8 bits, right? And you want to do like a word, right? So you would do an array index from. You can either do this. You can either do from 0 to 8, right? Or be like the CS people and do 0 to 7. Both of them are valid, okay? So I'm a MATLAB guy. I start with array indexing index 1. So that's what makes sense for me. But you guys did a lot. And I trust that the projects that I sent out to you guys, I'll get to it later. I need to get to that soon. Or what's this? Announcements. Let's see. Final project topics. Let me see. If I click on. I thought I sent you guys something.
Yeah, it's on the homepage.
Oh, it was in the home. Oh, okay. I remember what it was. Okay. Thank you. No, I put it right in the top. Yeah, there's a reason why I did that. Final project ideas. Okay. Possible student projects. Quad 2 input mux. Let me see. Quad 2 input mux, which means, let me see. Quad 2 input mux. Schematic. Hey, what does this look like? Busing, huh? Assignment 5? Not too bad, right? But then you'll have to design like the actual mux schematic, right? Let me see. Oh yeah, hey, transistor gates. That's an assignment I would have loved to make. Like that would have been assignment 6, transistor gate or transmission gates. So basically, how to send a bit, like clocking a bit. So from here to here, so you clock things in, clock. So CP tricks, okay? But yeah, you can design stuff like this. And what else is there? Multiplexers. Yeah, here's is this a multiplexer? Circuit diagram of 4x1 mux. But you need to do 4 of these, right? So what do? Build the raw mux, correct? And then just do the busing thing that we have. Cool. Let me go here. Clock doubling circuit using exclusive OR circuit. Hey. Wonder who did this one. So I'll tell you something about me. If you copy this, personally, I really don't care. There's a problem though. I'm an overachiever. So I took this like to a next level. And what did I do? Let me see. What's the next level did I do? Yeah, I did this, okay? Don't do this, okay? I went way too deep into this because I wanted to do a thing where you can tune the frequency of the VCO, the current starve inverter. So we designed a current starve inverter like this, like, hey, let's just choke this thing and like do this. So here's our thing, right? So I did a current starve VCO so I can change the frequency. Like, look, ooh, cool, right? And then what's his name? Current starve inverters, and I show you what's going on. I change the frequency. This is a really good project that I was really proud of it. Delay, 50% duty cycle, because the problem with doing a doubling circuit that me and my best friend, his name is Brian Kerstetter. You'll probably see his website. Let me see. Brian Kerstetter, CMOS EDU. Yeah, this guy. Oh, did he delete his pictures? Guess he did delete his pictures. Brian Kerstetter. Did he make a second one? Yeah, this guy right here. Laboratory reports. Oh yeah, this guy is in charge of making that CP301 board. You guys know what I'm talking about? UNLV, ECE, electrical. Yeah. See, is this one? Yeah, you see that guy right there? That's board right here. Yeah, this guy right here. This guy right here. The more you know. Okay. But yeah, let me see. Did he post this thing? Sorry if I'm going off topic, but electronics part. Ooh. He goes over the design. How he did it. The development board was using CP301 and CP310. And let me see what these hyperlinks do. Yeah, let me see. Click on this. Yeah. You guys have this manual? So yeah, here's the author. Cool stuff. This is stuff we do in our CMOS lab. Oh, yeah, he built this calculator. This guy's crazy. To create your own resistors. Anyways, I'm going really off topic anyways. This guy here and we realized the problem with the clock doubling. Clock doubling was the duty cycle was fluctuating. It's not 50%. It was going like 25% or 75%, depending on the input frequency. So we wanted to create a circuit that we can change the duty cycle so that if the frequency is low or high, we can adjust accordingly. So that was the problem. So if you copy what I did here, go ahead. I have the template for you. But I'm telling you now, it's gonna be a really tough project because I was doing a lot of cool work. Okay, what's another project? SR flip flop. SR flip flop with what did I say? With buffer with tri-state outputs. Is that good? And then we can design AND gates and OR gates. Let's see. OR gate. Transistor. No. CMOS. There you go. Cool. But this isn't an OR gate. This is a NOR gate. Yeah. That's a NAND. Because to do it, there it is. Okay, you see, this is a NOR, and then how do you make it OR? You put the inverter, right? Everyone understand what's going on? Easy stuff. Edge trigger T flip flop. We're here. Cool. What other circuits were here? Master, slave. There's so many things here. Okay, if you're doing a CP project, like the digital projects here, because I think a majority of these are all digital project. Personally, I would prefer to do that. It's easier. It just makes sense. The only problem you will have to figure out is like the what do you call it? Dr. Harris talks about in her 200 class and 300 classes about like what do you call it? Uh, Switching time, rise time, fall times. That's the only thing that matters with these projects. Okay, so be cognizant about that. The capacitance of an input, the resistivity of an output. Okay. Schmidt trigger. I guess you guys already did that, and do I want you guys redoing it again?
That was just my personal project.
Personal project.
Yeah, that wasn't class.
Could I say you could use it again? Well, if you use it again, well, you're just doing something. Yeah. It's not my. I can't really judge. Okay, but it's more like I would love for you to use this time to. It's more like I'm pushing you for a grade, but you're pushing yourself to put something on your resume. So if you're thinking if so, I'm a really fair professor, or not professor. I'm not even professor at all. I'm just your instructor. One day I'll be professor. I'm pretty fair. If someone cheats in a class, it's whatever. I can't do anything about that. But you're just cheating yourself out of an education. So when you go to the interview and say, "Man, I don't know who taught you your circuits. I don't know. Don't say my name or whatever, because I didn't do anything." If you don't fail me on the interviews, okay? Current star VCO, 2-bit bidirectional, P gate, buffer for driving up. Yeah, this picofarad low. This one, don't. Okay, I'll tell you something about these guys right here. It was impossible to get 20 picofarads. I think we were only able to get like how much? Like I think like 10 pico max, and those things were huge. So what's a heavy load? I don't know. Oh, wait, am I thinking right? You may, I guess, if you, let me see. Let me just look at something, okay? I wonder if I can do the following. I just want to get you guys happy with your My Library, File, New, Cell View, what do you call it? Analog tests. Okay? So if you want to do the following, be my very guest. I don't mind. I'm going to press I. I'm going to press analog lib. Let's see what is in this package. Cap. Okay, I guess you can use this. Right? Standard analog capacitor. I'm going to press I again. Standard resistor. R. Where's resistor? Elemental P. Q. R. Res. There you go. Guys like this? And then is it move and then rotate? Yes, there we go. And then what are we going to do here? I'm going to do GND, okay? Cool. And then I'm going to do VDC, yeah, vSource. Yeah, vSource. That should be fun. Yeah, lazy. There you go. Cool. Label VN. Label VOut. Okay. And then, you see. And then, by the way, was it Ferdos? For you, do you see how when I drag this label right there and you see how there's a dashed line? it's tying to that. So maybe, and I think I saw that problem where you were pulling this, but the yellow line was missing, right?
Oh yeah.
Something was wrong there. That was your problem,
Yeah,
okay?
I just deleted
Yeah, just delete the wires.
I did. It ended up working. Yeah.
Don't you like those silly funny things?
Yeah.
Headaches, right?
I think also another trick is just to pressing escape after you hit the label.
Yes,
Yeah.
it's
I was just trying to do the quick learning.
you know what? Let's let me do the thing. VN. Okay, so you did this right here, right? And then I did.
I just did I pressed C and then I copied it over.
Oh, and then you did.
Yeah.
I see,
And then change the name.
and then you did this, and then you did QV out, and then you did this, and then you see how it's not tied to anything. Yeah, that's funny. You see. Anyways, I guess there's two best friends you need to know: the Q button and the escape button. Okay, and maybe W. I don't know. There's a lot of. Do you guys like cadence when it works, right? V out. Okay. So let's just say you're a nerd like me, and you're like, ew, LT Spice. No, I'm gonna use cadence. Okay. Your guys' cadence expires. Licenses expire May 15th. Is that correct, or is it May 30th? When you guys log in, let me show you.
This is December.
December?
Yeah, December 30th.
Oh, okay. So probably Dr. Ming Zhu gave you guys an extra year.
It used to say never.
Huh?
It used to say never.
Never?
Yeah.
It shouldn't say never. It should say expire.
December 31st.
31st. Okay, because you were definitely his students. Okay, so. Well, for me, I make them expire at the end of the semester. It's more like that's the only time you can use the tool, because I only have 80 licenses, which means I have to make sure they all expire so that I can have another new student take the course. I only have very few spots I can give the never at license, so I'm a never person. Ming, I think Dr. Greg, that's Dr. Greg. Dr. Baker didn't want never. He likes having new accounts because he loves mimicking a student. He's like, I'm not using sudo. I'm gonna use a student account, and that's why I made a student account for myself, because I want to replicate all the problems you guys are doing. Okay. Anyways, I want to do something funny, or actually, before I do something funny, okay, launch ADEL. Okay, so you're a big nerd like me. Analysis. Choose. What should I do? Transient of. Let me do 10 milli. You guys like 10 milliseconds? You know what I'm gonna do? 1 micro. You know what my two favorite components are? R and C. And it's 1K, 1 micro. I think it's a pretty easy time constant. And for this guy, frequency name, I don't think that mattered. 1K. Turn it on. And then what's my amplitude? Amplitude is going to be amplitude 1. V peak. So 1 volt. You guys see that? Oh, there you go. Whoa. Cool simulation. Check and save. Right? What am I going to do now? Outputs. To be plotted. Select on design. Correct? I have the magic wand. Okay? So I'm going to click here and click here. How do I get rid of the magic wand? Escape. If you don't press escape, you're going to be sad. Okay? And play. Like that. So if you really want, if you don't like Pooey LT Spice, you can use the analog lib project, or the what do you call it? The library. And you can build components, okay? So these aren't real components. They're just simulations, okay? So let's just say I put here, I'm going to do something even crazier, okay? How do you bring your design into like a simulation? Just go to your My Library and bring, what do you call it? NMOS amplifier, analog tests. my inverter, whatever. Okay. Oh, doesn't it exist? Oh, great. I didn't create a simulation for that or a component. NMOS? It doesn't exist. Just plop it in there. Boom. Okay. Here's your project, or this is a bad example. Just one of the blocks. There you go. Okay. So these components aren't real, but you can simulate these components with things you built. This is a real part. Okay. Well, I already told you the cadence one is like a, what do you call it, a mathematically designed, but technically it's supposed to mimic a real device. So for all intents and purposes, this is a real piece. Yes? This right here is just imaginary. So if you wanted to drive a 10 picofarad load, so like a capacitor, like, let me see. I don't know what they call it, 10, I don't know, 1 micro UF cap. If you want to drive this with your chip, be my very guest. So this guy right here would be this guy right there. Okay. So I'm just setting you guys up that you can do everything in cadence. Even like any simulation you want. Inductors, capacitors with the analog lib. All right. Any questions? If I press save, you'll be okay. If I press check and save, just gonna cry for this guy. Okay. And let me just show you vSource. What if I do a? Can I do a? Let's see, pulse, exponential. Whoa. You guys want to do signals and systems? Let's see, zero value. What the heck is this? Okay, actually, I don't know how this works. Don't do that. Zero value, one value. Rise time, I don't know, 10 milli. Rise time constant, 5. Yeah, whatever. Check and save, run. I don't think this is gonna run. It's not gonna run. Yeah, of course it's not. Anyways, oh, it doesn't work. Sign. But you can see what I'm doing right there, right? Easy. 1K, 1 volt. Okay, let me see, because I think maybe the next week I'll talk about that, because I think today I just wanted to talk about final projects. Are there any questions about what I'm expecting? So the format, I'll get this for you guys later. Let me see. Which one was a good one? I think, for example, if your project was this 4-channel NMOS, but it's not going to be as easy as, or not NMOS, the NAND gate. All you're going to do is you're going to talk about, hey, just what are you doing, okay? What's the thing you're trying to implement? The application, okay? And then you're going to show off, like, this is what it is in real life. This is what people are doing, okay? There's so much literature. YouTube University. If you use Claude, ChatGPT's been funny. I don't think it knows how to do circuits. I made it do circuits. I hate circuits. I don't know. Talk to Dr. Zai. He's got an opinion. Anyway, talk about your circuit, okay? Build the schematic, okay? Tell me what you're trying to do, what you're trying to accomplish. Don't just put it in there and say nothing, okay? I want you guys knowing what's going on. You're going to give this to your Apple interviewer, okay? You're going to be like, this is what I did. This is how I can learn. Build your symbol. Make it look pretty, okay? And then I think I'm going to put a requirement. I might have to do this just in case. I don't know. I don't want to add too many new things on you. Just walk through this thing. Explain what's going on, because I'm going to be enjoying my coffee while I read this, okay? Lay it out. And yeah, just LVS it. And that's pretty much it. It's not that bad of an assignment. So do you see where the difficulty is going to come? It's more like the achieving the application. So my labs are supposed to teach you the tools, okay? But after this, you can build the components. So if you were to look at a lab like this, yeah, actually, if you want a template, don't really use it. But the way I have it right here, you guys see the part one schematics and the design decisions or discussions. See this right here? Why I did this? Here's the delay block. I talk about it in full steps. Here's this. I look, figure 6, figure 7, effective resistances. I talk about all these little things. So like if I show this to the Apple employee or the manager, they'll be like, wow, you even talked about the output resistances. Do you guys know about the output resistances of the transistors? Right? Dr. Ming Zhu talked about it, right? Output resistance. Good. Like go through all this stuff, like boom, 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 test all your components, simulations. Now here's your final project right here. Oh, come on. That's your final project right there. And then here's your simulation. Sim my final project, or sim, I don't know, David's project, final project. Okay? And then I did a parametric analysis because I like that. Show what you're trying to do. Okay, don't just paste something and expect me to learn. Okay, I want you guys to teach me what you guys are doing. You're going to teach your Apple employee or employer, Micron. They already know all these circuits. They just want to know if you know what you're talking about. Okay, so don't think like, hey, just you learn it. Anyways, and if you do this right here, how to improve our initial design, depends. This is your research project, okay? So technically everything above here is technically what I would expect as a final project. Everyone see what I'm trying to say? So if you wanted to copy this, be my guest.
That's the layout, though, right?
Oh yeah, there's a layout, but right here, I just talk a little deeper about the initial design, because in your schematic you're testing your component like heck, like going crazy. Why would I want to lay out a project? Because like I didn't want to build 2 projects. I wanted to like improve the schematic even deeper, because once you finish your schematics, you're done. Just push them away. Now just paint it. Okay, so that's why I did like this, because I said after this I talk about, okay, here's my simulations part 2, and even changing the power supply. So basically what I did right here was I said, okay, I made the power supply, what was it? Changing the power supply, 10. Oh, so what did I did here? You see how we have a VDD pin, right? So you know how you have a battery, like a 9-volt battery in your backpack, or like what do you call it, your iPhone battery? How does your circuit respond when it's dying? So instead of it being 9 volts, it's at 8 volts. If it's 7 volts, 6 volts. When does your project fail? Yeah, actually, if you put that there, I'll give you good kudo points. Okay, like you'll be great. So basically, tell me how to break your project. Okay, maybe I'll put that as a requirement. Tell me when does your project fail. Okay, so do these little tests. Change VDD from 1.1 to like, I don't know, 0.8, or overvolt it, because you know what overvolting does? Breaks things too. So like maybe 1.5 or 1.8. Let's just say you put 1.8 volts, and what happens if you use one process's voltages with another So I think this process, we have the 2 volts, right? NMOS 2 volts. And I think it's 1.8. I think so, right? I mean, let me see. I'm not so sure either. Close. Save state. Sure. Boom. And then, yeah, save. Whatever. Where was it? Analog tests. If I press I to instantiate, GPDK, NMOS 2 volt. These puppies. But I don't know the voltages. So if you go to the homepage right here, I give you guys the manual, PDK reference manual. What are we gonna do? We're gonna press Control F, NMOS2V, 1.8 volt nominal voltage. So what does that sound like? A lot of CP stuff, like 1.8 volts is a nice voltage. But we use the smaller one because I want to go faster, okay? Smaller processes are faster, larger ones give you more gain. You have a lot more wiggle room to play with. So if you want to use the NMOS 2 volts for your projects, also be my very guest, okay? All these parts here can be used, but just let me know how that works. Any other questions? Let me see. Maybe I should have pulled out this guy. Let me show you some other things I wanted to show you. So here's a CMOS mixed signal design book right here, and I really like this book. If you want to implement something from here, analog filters, digital filters, let me see, pendulums, track and hold. Let me see if there's any good circuits in here. Do I want you building this? Maybe. Ooh, yeah, clock dividers. Components of a decimation block. Nice. Sample and hold. Or actually, let me see. Project. He doesn't use the word project in this book. Cool. Ooh. Single-ended sample and hold operation. Ooh, that's a nice circuit. What else is there? Interpolation. Yeah, stuff like that. There's a lot of cool K-path sampling. Oh yeah, this is his final project right here. He made us do KD1S. Let me. Okay, I'll brag a little bit. CMOS CDU. That's me. Projects. Click on there. Mixed signal design project. K delta 1 sigma. Noise shaping modulation. But yeah, this is a hard project, not gonna lie, it was tough. And I go over signals and systems and how to build this. Clock generation, what do you call it? This right here is a current starve, what do you call it, in VCO? Yeah, this is another type of current starve VCO. Where the frequency was a function let me see, the voltage here, voltage control oscillator. Anyways, I go over a lot of things here, but I don't know. There's a lot of information, but are there any questions about that too? What are the projects? You see chip layout, memory cells. Oh yeah, you'll see DRAM. If anyone wanted to do a DRAM cell. See DRAM, VSLI. Yeah, this is a really good book to get. Chip organization, peripherals, memory cells, SRAM cell. Okay. Your access MOSFET. These are transmission gates. Okay. And this right here is, well, this is your cell. Word line tied here, bit line, because I'm trying to read things from memory. And that's your layout, that's your answer. You like that? Not that hard. And then test it and then just tell me what it does, okay? Let's see what it says. The sizing of the access MOSFET is important. If they are too weak, the bit lines won't be able to flip the state of the cell. If they're too strong, the layout area can be very large. Okay. To reduce the layout area, a cell that doesn't use PMOS devices can be used. Okay. Eliminating the end wall and using high resistance poly. Okay. Remember in the, what do you call it? Our GPDK, right? There was those really high resistive resistors, but they were small layouts. This is what Dr. Bego was talking about. If you use high resistive poly resistors, he was like, screw these PMOSs because the wells are so huge. Replace them with a tiny resistor and boom, gets the job done. So, read-only memory, ROM cell. Yeah, stuff like that. You can build this. I like this right here. Floating gate memory. I don't think we can do that in here. Threshold voltage. But yeah, this book has a lot of study about what not to do, what to do with flash memory. Does he talk about it? Yeah, you can't do flash memory because you need this double. There's some processes that do have this double gate thing where you can store the charge here and read it immediately like that. It's super, super cool. That's how flash memory works, where the charge is right on the gate. You just kick that electron and it just sends it. That's why this thing is super fast, but it gets super expensive too. And then layout of your flash memory. Yeah, there's a lot of cool things here. Let me see. Additional reading. Let me see. Is there other things here? Delta sigma modulation. Let me see. Is there anything else I want to show you? Give me a second. Special circuit. Ooh. Chapter 18. Okay. Schmidt triggers. Right? If you want to build a Schmidt trigger for your project, okay, talk about it. What's going on? Here's your input. Here's your output. Boom, boom, boom. Okay? Here's a cheat sheet. Go home. Portion of the Schmidt trigger. Use to calculate. Talk about this. Tell me why it works, okay? Don't just put things together and say, I did the project. You'll get the grade, but do you understand what's going on? Okay? I want everyone to make money here. What other projects were in here? Multi-vibrator circuits. Let's see. If you want to do this right here, monostable multi-vibrator, astable multi-vibrator, input buffers. Let's see. Ooh, input data. So for you CPs, goes up, goes down. Decision level. If the decision level's here, it's nice. Boom, you get really correct pulse widths, okay? You see, here's our pulse, right? This is 0 right here. This is 1, 0, right? But for this one, it's like, here's the 0, 1, and it's decision level's too high, decision level's too low. We got to get the correct thing. Does he talk about it? Input buffers? Consider waveform. Does he talk about that? Basic circuits. So yeah, could this be a good circuit? Skew and logic gates. Ooh, this is an interview question, by the way, asked at Micron, which was what do you call it? Which input has which for a NAND gate, right? Which input will result with a higher what do you call it? Skew rate or something like that, or rise time or something like that. B or A. With A, you have the body connection, right? And Dr. Mings, you talk about source body voltages of an NMOS and how that changes the threshold voltage? No? No? Point is, the body right here is connected to ground, right? And then the source is connected to ground too. So VSB is 0 volts. So the threshold voltage is going to be, well, the 0.8 that we found from, was it called Lab 1? Suppose the source voltage isn't ground. It's like, I don't know, 0.5 or something like that. So your body voltage is going to there's going to be a voltage, which means your threshold voltage changes, which means it's going to be harder for B to turn on this than this. So do be wary about that. Here's your output. You see, input connected with B to B with A high, B high. Skew introduced by using different inputs. But yeah, using 2 NAND gates in parallel to reduce input dependent skew. So you see this right here? This is probably the NAND gate that they probably use maybe for like really like high fidelity circuits. So do you see this? You see? Okay, I'm gonna be that professor. You guys like this? He's using paper and pencil. Let's see. Bum, 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 bum. Let's see. Um. Ah. What's that right there? NAND gate, right? What about that right there? Also NAND gate, right? Not that bad. So all he did was like, oh, just switch the A's. Like the A is right here, and the A is right here, and then the B is over green is over here and over here, and then vice versa. So PMOSs don't care, but the NMOSs do. All right, that's what Dr. Baker is talking about. Differential circuits. Ooh, this is cute. You see, there's a lot of cool circuits here. Ooh, rail to rail buffer based on, yeah. This right here is like, see, you can make some really cool circuits here. This is what I'm talking about. DC references, reducing buffer input resistance, charge pump. If you want to build a charge pump for your final project, it's right here. Let me see what other projects were in here. Example, simple substrate pump, NMOS driver. And yeah, and then, oh yeah, DPLLs. So I think someone wanted to do that. If you want pain, oh no, was it the APLLs, right? If you want pain, be my guest. But DPLLs are a little more simple. But this is your research project. But if by next week, like next Thursday, you're like, oh shoes, I haven't like gotten to the like, or I'm still working on the scheme. If something's working, I don't know.
I'll start on it, and like, say I have one section done, and I think it's too hard, I'll just stick with that section.
Probably, okay? Because I want you guys making things that work, okay? Phase detectors. Ooh. XOR phase detector. So detect the phase. Here's your circuit. Phase frequency detector. Ah, that one's cool. Okay? And he does a study on that using tri-state and charge pump circuits. Okay? Voltage controlled oscillations. Okay? Talk about this, have fun. Current star VCO. See, stuff like that. Easy answers. Let me see. And then you'll notice that there's it's an exponential when you go up and down for the voltage. So the way the linear, or what do you call it, make it more linear, where as the voltage goes up, the input voltage, the frequency should also be linear. So you would do something like this, where this is like super wide or something, okay, to reduce that threshold voltage, okay. Source coupled VCOs. Wow, there's so many. Like this chapter right here is filled with like nuggets of like filter. It's like, or nuggets of information. Just X or DPLL. Here's your final project. Look, this looks like a final project there. That looks like a final project there. That looks like little hard, huh, Payson?
A little bit.
If you do this would actually be pretty cool. I think lots of companies would definitely love to read this. Okay, so if you do those special circuits I showed you right here, where's my DPLL? A DPLL right here, and here's some conditions. Would I tell you to follow these? Try to make it more realizable, okay? Because I know this right here, this DPLL is using Dr. Baker's CMOS EDU parameters, okay? So they're using the 1 micron and the 50 nanometer process? I think so. So in the end, just try to make it, try to push the limits of your component, okay? Make sure it's like a realizable, like if you can get to like a gigahertz, like, oh, a DPLL that works at until like a gigahertz or maybe 10 megahertz, because this right here is for an older process. So for a newer process, I would assume you have to beat these specs. Generate a 4 megahertz output. So yeah, 1 gigahertz to 4 gigahertz output. Okay, just, I don't know, multiply by 10. But I don't know what he designed this for. It was 50 nanometers or 1 micron. But point is, faster than this, okay? The output should follow the input frequency for changes from 900 kilohertz to 1.1 megahertz. Discuss the transient properties and detailed design of the phase. Yeah, the three mini projects in one project. Okay? Entire design should be monolithic. That is, no external components should be used. He's vicious, huh? Well, not vicious. He's just, going right for the point of the class, which is, can you do CMOS EDU? All right, I believe you, but just let me know, okay? I want these projects to be not too easy, where Apple's like, what the heck, but not too hard, where also Apple's like, well, you didn't finish the project, okay? Let me see, XOR phase detector, Let's see, PFD DPLL. What is that? What is PDF or PFD? Yeah, it's okay. Phase frequency detector. Not that bad. System considerations. You guys like how I'm just pointing and clicking? Jitter. I know jitter was a problem. Let me see what else is there. Practical VCL, VCDL. I want to talk more about layout, but honestly today I'm just trying to get everyone introduced to the final projects. Current mirrors. Let's see, you guys know how to do that. There's a lot of cool study with current mirrors. Amplifiers. Let me just talk about this. Today's a CMOS EDU day. Frequency response. Let's see, Give me a second. Class AB amplifier using an inverter output structure, push-pull. Talk about how it does Class AB amplification from Dr. Ming Zhu's class. Remember that? I was there for that. It was a pretty cool lesson, okay? So if you want to do a Class AB amplifier, just tell me what it does, how to break it, the gains, all that other stuff, how much power, the efficiency. When VDD is 10%, like 10% less than VDD, or when your supply is less than 10% and more than 10% of VDD or something like that, okay? Just break your thing, have fun. DC operations, let me see. Distortion's a good one. Diff amps, very important. See if he talks about something important. Because I know I want wide swing differential amplifiers. So basically, you'll notice with diff pairs. Have you talked about diff pairs in the class? Right? If you do an NMOS diff pair, it's gonna have a hard time. What was it? The input. You can't read the input until it hits the threshold voltage. So let's just say from 0 to 5 volts, right? But the NMOS doesn't turn on until 1 volt. So everything from 1 volt to 5 volts is readable, but not that 1 volt. For the PMOS, it's the opposite. It's from 4 volts to 0 volts, but not the anywhere. So if you use point is, if you use an NMOS and a PMOS together, now you can read the full range, wide range, wide input swing, so that you can see the full dynamic range. So the smallest little signal to like the biggest swing. Yeah, stuff like that is good. Constant transconductance diff amps. I'm just talking about problems. There's a lot of homework. Voltage references. I had a student who wanted to do something like this. BMR. I forget what that means. Beta multiplier. Yeah, beta multipliers. Someone wanted to build. If you wanted to build this as a final project, let me see. Let's see if he talks about it. Short channel BGR. Does he talk? I guess he doesn't talk about it. Interesting. Or maybe it was a different chapter. It's okay. Operational amplifiers 1. This would be a 420 lab or 420 lectures final project. Dr. Baker made all his students do an op amp for the final project. So the answer would be in his book. You just gotta do it. So let me show you the final answer for Dr. Baker's project. Was it this one? I think it was that one. Let me see. I think this was it. Yep. This is Dr. Baker's final project. Basically explain what it does, the uh, all the properties. So he gives you the answer. He knows what he's talking about. But the problem with analog design is you can really make it a really like hard project if you don't hand calculate things. If you don't know what you're doing and you're just changing the W's and the L's, you're gonna struggle a lot. Okay, I'll tell you that. Funny enough, when I was taking 420, I struggled a little bit with this because I didn't know what a real part was until I took 421. Because 421, he made the part realizable, so like the small size, like how we're doing it, with how I'm teaching you guys right now. You guys know what to do. But for me, I've never done layout because Dr. Baker never taught layout in 420. His job was to teach pure analog. So he didn't tell me that, but once you know the layout and connect the schematic, it was more like a light bulb for me. So I had a friend teach me 421 a little bit, and then I was able to master that final project. So if you copy the circuit, be my very guest. But the hardest part of the project is going to be solving for the sizes. And that's going to take like weeks if you don't know how to hand calculate that, okay? And then, yeah, you have to generate these plots right here. Let me see. Does he talk about? Oh, no, it's in chapter. Let me see. Dynamic analog. Switch capacitor. Ooh. So Dr. Baker does a thing where, let me see. See this right here? That's a transmission gate. I want to teach you guys that, okay? Transmission gates are really cool. They're really simple, where you have a PMOS and an NMOS, and you're just controlling the circuits. So when one turns off, the other one turns on, or you turn off the NMOS and PMOS with a 0 and 1 and force them open. It's really, really cool. So Baker says, there's a way to have a variable resistor in CMOS processes by having a transmission gate and a capacitor, and it looks just like this. Yeah, see that right here? That's what he's trying to show you there. It's a really, really cool study. And if you put this on your final project, this right here is a hireable job too, okay? But yeah, RC. You guys like this RC filter right there? Remember the first thing I did earlier today? This is an RC filter too, where this right here, this R, is tunable with this resistor right there. You guys like that? Switch capacitor integrator. See? You could have a variable resistor, and here's your fat capacitor. Parasitic insensitive. Other integration. There's a lot of crazy things in here to I don't expect everyone to like master all this, but yeah. Oh god, let me show you what I was talking about. Why I was saying things. Oh yeah, here's an answer. You see, was that it? I think that was it. Self-bias reference. So if you're trying to build a MOSFET or what do you call it? What's his name? An op amp, you need to have biasing voltages. So this right here, you remember that V bias N and that V bias P? This right here is the big daddy circuit, okay? This is where you can get some really, really cool circuits, okay? And these two voltages can be used to get the right current. You see this IREF right there? The reference currents? This V bias P and this V bias N, if you connect the PMOS like this and this, you'll get that 20 microamps or whatever you need for your projects, okay? Basic concepts. You see, and I think I'm going to end very soon because honestly, I want to leave it up to questions, okay? Step response. If you're doing an op amp for the class, I'm going to expect you guys to do, don't do that one, or if you want to, go ahead. What's it called? PSRR. I'm looking for PSRR. Power supply reject There we go. Power supply rejection ratio is basically the gain, right, as a function of frequency divided by this other gain right here. Okay, you have a plus and you have a minus because you have VDD plus, you have VDD minus. And you can do this test. This is how you test your op amp. So you wiggle it up here, you wiggle it down here, VDD, and you just watch that, what do you call it, PSRR, okay? And then, let me see, common mode rejection ratio. Let me see, where is that talk? Common mode. There it is. Common mode rejection ratio, okay? How do you test your op amp for that? This is how you do it right here. You get your real op amp right here, okay? This is your real op amp. This is the piece you built, okay? And you're just doing this type of simulation, okay? And then the ratio, where's the ratio? Is basically, what do you call it? This gain over this gain. 80 over AC. What's 80 over AC? Anyways. Are there any questions about that? So point is, what's the outcome of what I'm trying to mention? I'm talking about all this stuff about CMOS. There's a lot of cool projects you can do. Is everyone seeing all the magic? Okay, so I had someone ask, like, can I do just a simple like a logic gate? Like I'll build a NAND, a NOR, a XOR, like the way we did it for 320. Yeah, but you're gonna have to do something with that, okay? I want you doing something like if you build a MUX, like a 2-channel MUX that controlled all the things and be my very guest. But it's whatever, okay? I want you guys doing some real valuable projects. But if you do something impossible, like okay, if you do, let me see, where's that scary circuit? If you do something like, I don't know, like this, where is it? Come on. Yeah, if you do this circuit right here, where is it? Yeah, something like that. Cascode differential amplifier. This is cool. I like it. But I need you to know the analog stuff, okay? Because I know the analog too. It's been a while, but it's not that hard for me to get back into it. So, but yeah, my job was to teach you guys the cadence. And I think I did a good job. We'll see about how tomorrow's things is. Once you guys publish your Lab 4 and Lab 5, I'm going to grade on as soon as I can, okay? Maybe I'll stay up at midnight or something, okay? I know. I'll sleep too, okay? I promise. Any other questions before I end the video? All right, have a good day, everyone.